All right, so in our last lecture, we talked a little bit about atomic theory and the development of that, some scientists, what they discovered, all that sort of stuff. So now we're actually going to get into some of the heart of the atomic structure and the parts of atoms. So there are over 100 types of atoms. That's your elements. That's your periodic table. We're going to do a whole chapter just about the periodic table. And the one thing you should know is that they differ by the number of protons. Remember, part of Dalton's theory was that atoms of the same element are identical. And I said that that's not exactly true because they can differ in the number of neutrons in nature. But if it's hydrogen, it's going to have one proton. That's never going to change. And so the number of protons in a specific element will always, 100% of the time, be identical. So some atomic vocabulary. First of all, the atomic number is the number of protons. All atoms we assume are electrically stable in nature, meaning they're neutral. So the atomic number and the number of protons will also be equal to the number of electrons, because a proton has a +1 charge and an electron has a -1 charge. So atoms we assume are neutral. So the number of protons is equal to the number of electrons. The mass number, and this is a whole number, is the number of protons and neutrons combined. So for a particular atom, a single atom, you would have a mass number. So for example, carbon 12, 12 is the actual mass number in this atom right here. So carbon 12. And it turns out carbon 12 has 6 protons and 6 neutrons. Now it doesn't say it here, but it would also have 6 electrons, because if carbon is neutral, then the positives and the negatives need to cancel each other out. So the protons and electrons would be equal to one another. Carbon 13, which is another isotope of carbon, we're going to talk about isotopes in a minute. Carbon 13 has 6 protons and 7 neutrons. So again, this is the mass number here, and this is how many protons and neutrons. And notice, because it's carbon, the number of protons has to be the same. Carbon 14, which happens to be a radioactive carbon, it also has 6 protons, but what changes is the number of neutrons. And again, it would have 6 electrons, 6 electrons. So the protons and the electrons, unless they tell you otherwise, are going to be equal, unless it's an ion. An ion is an atom with a charge, and we'll talk about that. But the number of neutrons, notice that can change. And also make sure you know what this number means, this isotope notation, that this is called the mass number. So here are just some examples. Notice oxygen 16 has 8 protons, and if we wanted to figure out how many neutrons, we would subtract 16 minus 8. There would be 8 neutrons. Oxygen 17, so this has the mass number is 17. The number of protons, the atomic number is 8. 17 minus 8 gives us 9. And so this one would have 9 neutrons. And I'm using the little notation for a neutron, in with a little 0, because it doesn't have a charge. And then here's our carbon. So this is actually called AZ notation sometimes. AZ, and then the element would be element X, okay? So the Z would be the atomic number, which is going to be your number of protons. And then A would be the mass number, which is going to be the protons plus the neutrons. Notice in this symbol, the number of protons is also indicated. When it's written this way, oh, sorry about that. When it's written this way in this symbol, the number of protons, going back to here, you don't know the number of protons. Like carbon 12, it doesn't tell you how many protons. So you'd have to go to the periodic table, because the periodic table would have that, because actually that's how they're in order on the periodic table. They are in order by their atomic number, or their number of protons. So if you look at the periodic table, number 1 on the table, which is hydrogen, it looks like this, and then you skip all the way across, and then number 2 is helium, and you'll see a 2 here. So that is going to actually be your atomic number, which again will be the number of protons. Okay, moving on. So here's an example. So find each of these. So the number of protons. So this is the AZ notation. So since the number of protons is going to be this, the Z, again, I'll write it like this. So AZ, this is bromine in this case. So the Z is going to be your number of protons. It is also the atomic number. So the atomic number is 35. The number of protons is 35. To get the number of neutrons, we have to subtract. So 80 minus 35 gives us 45, right? So 45 neutrons. The number of electrons is going to equal the protons unless you see a charge here. So we're assuming if there's nothing here, we assume it's neutral. So the protons and electrons will equal out. And then the mass number is going to be 80. So I know I went through that very quickly, but we're really just summarizing what we did in class today. All right, so for practice, here's the second one. Oops. An element has an atomic number of 34. So we can find it on the periodic table. This is going to be the number of protons it has. And on the periodic table, again, if you look at the periodic table, in the boxes, you know, this is going to be 1, and then 2's over here, and then it's going to be 3, 4, etc. The number in the box, the top number, that's going to tell us what element it is. And then they gave us a mass number of 78. So remember, this is going to be the protons plus the neutrons. So first, number of protons, 34. The number of neutrons is going to be 78 minus 34, right? So that's going to be 44. So that's going to be our neutrons. The number of electrons, remember, these two will always be equal unless it has a charge, so 34. And now the complete symbol. So they want that AZ notation. So we're going to put we're going to put 34 down here. We're going to put the mass number. Be careful. Some people mess up and put the number of neutrons up here. 78. And now we need to know what letter it is. What element is it? So we go to the periodic table. We find number 34, and that is selenium. So we write our symbol Se. And this would be the full symbol. And this is something you would have to do on your test. So make sure you know what goes in each spot, how to figure out what element it is, how to get protons, neutrons, electrons, mass number, atomic number, all of these. All right, here's one more. So it has 91 protons and 140 neutrons. So let's start with the atomic number. That's going to be 91. Now, careful. Some people in class mess this one up. The mass number is not 140, right? It has 140 neutrons plus 91 protons. So you have to add those together. And that's going to give us 231, right? Yes, 231. So that's going to be our mass number. So we're going to do this 91, 231 up here. Number of electrons we're going to assume also is 91 because it's going to be the same as the mass, the atomic number, or the number of protons. And now we need to go to the periodic table and find number 91. And again, they're in order, so this is really easy to do. It's all the way at the bottom. And that looks like it is protactinium, Pa. And this would be your full symbol, sometimes called the AZ notation. Okay, so what are isotopes? So I mentioned that sometimes atoms that are of the same element can have different numbers of neutrons. And so their mass numbers are different, even though they have the same number of protons. They have to have the same number of protons, or they're not going to be the same element. So most elements have 3 or 4 isotopes in nature. Some only have 2. I think chlorine only has 2. But hydrogen, for example, here has 3. In fact, hydrogen, they actually have special names, the 3 different isotopes. Most of them, they're just called like hydrogen 1, hydrogen 2, hydrogen 3, or carbon 12, carbon 13, etc. But hydrogen, there's special names for these. Anyway, so those are what isotopes are. And again, this is the way we name them. So like carbon 12 is the one, this is the mass number, and it's the one with 6 protons and 6 neutrons. Here's carbon 14, 6 protons, 8 neutrons. Now, ions, unlike isotopes, ions are atoms with a charge, and that happens only because they have extra or missing electrons specifically. So this changes how we write the notation. We write the charge in the upper right corner. And there's actually special names for positive versus negative ions. A positive ion is called a cation, and a negative ion is called an anion. Sometimes people get mixed up with this because when they see a positive charge, they think add. Of course you do. You think plus means add. But remember, electrons themselves are negative. So if it has a positive charge, it's actually missing electrons. So let's take a look at this. So sodium, this is a sodium ion. So if I find sodium on the periodic table, and let's say you wanted to know how many electrons this sodium ion has. So if I go to the periodic table, sodium is number 11. So if it had no charge at all, it would have 11 protons and 11 electrons. So 11 protons, and then, but notice the plus charge. that means it's missing an electron. So it actually only has 10 electrons. And again, the reason why is because protons are positive. Electrons are negative, right? So if I do 11 minus 10, I get a positive 1 charge. I have a plus 1. I have 1 more proton than electrons. Now we see chlorine. The ion is actually called chloride. And chlorine on the periodic table is number 17. So it would have 17 protons, but notice a negative charge. That means it has 1 extra electron. So this is going to be 18 electrons. Oxygen, this is oxide, it's called actually, and this is an anion. It has a negative 2 charge. So if we look up oxygen, it is number 8. So it has 8 protons, 2 extra electrons. That's going to be 10 electrons. And then aluminum, our last one, we go to the periodic table. It's number 13. So it's going to have 13 protons, but it's missing 3 electrons, so 10 electrons. So proton, sorry, this is the proper symbol there. All right, so make sure you understand that. That's a common mistake people make, is they go the wrong way. They think, oh, add, that means I need to add an electron, or minus, I subtract an electron. But remember, electrons are negative. So it's sort of the opposite. If it has a positive charge, it's missing electrons. If it has a negative charge, it's got extra electrons. Okay, atomic mass. So atomic mass, this is the last concept in our notes. It is the average of all the isotopes in nature and their abundances. And this is usually a decimal. So if you look at the periodic table, they wrote atomic weight here. Usually it's called atomic mass, but this is the decimal. Now, why isn't this a whole number? If I was to find 1 atom of krypton, the chance that it would have a mass of this is 0%. Sort of like if I said, hey, what are the chances you walk into, if the average number of students in a class at our school is, let's just say, 30.7. What are the chances you come into a classroom and that classroom has 30.7 students? 0%, right? There's no chance there's 0.7 of a student in a single particular classroom. So that's why mass number and atomic mass are different. The mass number is going to be a whole number for a single atom, but the atomic mass is going to be an average, and that's why it's a decimal. So you can't have an actual atom that has this mass. That's a very important concept for the test, literally. I could ask you that. I could say, hey, what are the chances I would find an atom of krypton with a mass of 83.8? And a lot of people would be like, oh, it must be, it's very common. But the answer is none, 0. Just like you can't find 30.7 students in a classroom, you cannot find a krypton that has a mass of 83.8. That's an average. All right, so the way that we calculate it by how common they are. And I'm going to run out of time in this, but notice how carbon-12, most of the carbon-12 in nature, 98.89% of it, of the carbon in nature is carbon-12, has a mass of 12. And that's why if I get the weighted percent average of these, the actual atomic mass of carbon, the decimal, is 12.011. If most of the carbon in nature had been carbon-14, then the decimal would have been closer to 14. So that's how we figure out atomic mass. And you can actually calculate it. I'll show you really quick. So element X has 2 isotopes. What you're going to do, I'll do it really fast, is you're going to take these and you're going to change these fractions to decimals. It's going to look like this. You're going to multiply each one by its relative mass. You're then going to, so your relative abundance, you're going to add them together, and this would give us our atomic mass. And you can actually go to the periodic table. If it's a real element, it turns out, in this case, boron actually has this atomic mass. So you could actually identify what element it is based on that average atomic mass. So I'll repeat that because I did that really quick. So you're going to take the masses, and it can be more than 2. So this one had a mass of this many AMU, and our units would be AMU on this, by the way. This would be this many AMU. Change these to decimals, your percents to decimals. It's just how you multiply out to get percentages of things. And then when you add this up, you're going to get this. This is another thing showing the work for the same thing. And we're going to do some practice problems on this today, so maybe I'll try to post a video of just me doing some more practice problems. And there's also a bonus. Again, I'll try to show you this bonus one in the video. This is working backwards. where you don't know the relative abundances. So I'll show you this in another video.